sleep occurs in all mammals and probably in all vertebrates. We crave sleep when deprived of it, and to judge from some animal studies, continued sleep deprivation can ultimately be fatal. Why do humans and many other animals sleep? To feel rested and refreshed upon awakening, must adult require 7, 8 hours of sleep, although this number varies among individuals. As a result, a substantial fraction of our lives is spent in this mysterious state. For infants, the requirement is much higher, 17 hours a day or more, and teenagers need on average about 9 hours of sleep. As people age, they tend to sleep more lightly and for shorter time at night, although their need for sleep is probably not much less than in early adulthood. Thus, older adults often make up for shorter and lighter nightly sleep periods by napping during the day. Getting too little sleep creates a sleep debt that must be repaid in the following days. In the meantime, judgment, reaction time, and other functions are in varying degrees impaired. Poor sleep, therefore, has a price, sometimes with tragic consequences. What the leading cause of death in late-stage teenagers in throughout most developed nations? HIV takes third place and suicide takes second place. At the first place are car crashes, and here sleep matters enormously. Good example comes from Wyoming. They shifted their school starts from 7:35 a.m. to 8:45 a.m. and then they measured the reduction in car crashes in this narrow age of just 16 to 18. ABS technology, what we call anti-lock braking system, that prevent your wheels from locking up and hard braking, so that you can still safely maneuver a vehicle that dropped accident rates by 20 to 25%. But here is a biological factor, sleep, that will drop accident rates by up to 70%. Sleep, or at least a physiological period of quiescence, is a highly conserved behavior that occurs in animals ranging from fruit fly to humans. Circadian rhythmicity of core body temperature, and of growth hormone and cortisol levels in the blood. In the early evening, since it's generally colder at night, our energy would have to be expended to keep warm, were we nocturnally active. Body temperature has a 24-hour cycle reaching a minimum at night and thus reducing heat loss. Core temperature begins to decrease, whereas growth hormone begins to increase. The level of cortisol, which reflects stress, begins to increase in the morning and stay elevated for several hours. One of the most exciting hypotheses is that sleep makes an important contribution to processes of learning, memory, and brain plasticity. The notion that sleep plays an important role in learning and memory has been around for over 2 centuries. In 1801, scientists proposed that dreaming may alter the strength of neural associative memory links. Following this hypothesis, the first systematic assessment of sleep and memory was conducted over a century later, in 1924, when it was shown that, compared with time awake during the day, memory retention was better after a night's sleep. Sleep-dependent memory processing as a specific concept, however, is a relatively new theory for which a large number of studies over the last 10 years, spanning most of the neurosciences, have provided supportive evidence. The development of a concise singular description of sleep-dependent memory processing is made more difficult by the complexity of what constitutes sleep and memory. Sleep is frequently described in two broad states: rapid eye movement sleep (REM) and non-rapid eye movement sleep (NREM). Similarly, memory is not considered a single phenomenon but broadly split into memory types and memory stage. Humans have at least two qualitatively different systems of information storage, which are generally referred to as declarative memory and non-declarative memory. Declarative memory is the storage and retrieval of materials that is available to consciousness and can be expressed by language. Examples of declarative memory are the ability to remember a telephone number, a song, or images of some past events. Non-declarative memory, on the other hand, is not available to consciousness, at least not in any details. Such memories involve skills and associations that are by and large acquired and retrieved at an unconscious level. Remembering how to dial the telephone, how to sing a song, or making the myriad associations that occur continuously are all examples of memories that fall in this category. It's difficult or impossible to say how we do these things, and we are not conscious of any particular memory during their occurrence. Memory stages include several phases, including encoding, consolidation, integration, recall, and even erasure. Because there are a number of different sleep stages and memory stages, the number of dynamic ways that various sleep states may interact and influence different aspects of memory is considerable. In a study by De Koning and colleagues, polysomnographic analysis before and after an intensive language course indicated that changes in sleep structure takes place during learning and that these changes are correlated with knowledge acquisition. This result indicates that the act of learning can affect sleep and produce changes in the structure of subsequent sleep. With this in mind, does the relationship work both ways? That's, does sleep affect learning? In addition, many studies have demonstrated that sleep after learning improves memory performance. In the study, motor skill performance was tested following offline time delays. All participants were trained and retested, but variations in sleep conditions between the groups were imposed to determine the consolidation benefit of 1. Wake time, 2. Wake time followed by sleep, and 3. Sleep, then wake time. Large and significant enhancements in motor performance between 19 and 21% were observed after a night of sleep. Improvements in performance were observed in individuals who slept immediately after training and those who initiated sleep up to 12 hours after training. While the merits of sleep after learning have been clearly demonstrated, it has become apparent that sleep before learning is also critical for brain function. The importance of sleep before learning has been demonstrated in humans by Yo and colleagues examined the functional relationship between the hippocampal defects produced by deprivation and memory encoding. Study participants were either deprived for one night or allowed to sleep normally on the evening before the memory encoding task. A pilot study involved viewing positive, negative, and neutral words presented to subjects, followed by a recognition test 2 days later after recovery sleep. When combined across all stimulus types, individuals in the sleep-deprived condition exhibited a striking 40% reduction in the ability to form new human memories. However, when these data were separated into the three affective categories, negative, positive, or neutral, the magnitude of encoding impairment differed across categories. In those who had slept, both positive and negative stimuli were associated with a superior retentional levels relative to the neutral condition, consistent with the notion that emotion facilitates memory encoding. This selective alteration in memory encoding may provide an experimental explanation for the higher incidence of depression in populations expressing impairments in sleep, which, due to these specific defects, may suffer a negative remembering bias despite experiencing equally positive and negative reinforcing past events. The impact of sleep deprivation on the neural dynamics associated with encoding of new declarative memories has been reviewed using event-related fMRI. In addition to performance encoding impairments at a behavioral level, a highly significant and selective deficit in encoding activation was reviewed in bilateral regions of the hippocampus in the sleep deprivation condition, a structure known to be critical for learning new episodic information. Thus, sleep is not only important after learning for the subsequent consolidation of memory, but sleep before learning appears equally critical in preparing key brain structures for efficient next day memory formation.